Hello, my name is Julien Lange and I'm going to talk to you about fair refinement for asynchronous session types. This is a joint work with Bravetti and Gianluigi Zavattaro. Nowadays, message passing over FIFO queues is omnipresent. You can see that in programming languages like Go, Rust, Erlang, but also in middlewares like Apache Kafka, RabbitMQ, these sort of things. It's convenient to reason about these systems using either communicating finite state machines or asynchronous session types, which are really good abstractions to reason about these systems because they really focus on the problem at hand. The problem is that these formalisms are Turing complete, so most properties are undecidable for them. And a key question we are trying to answer in this work is how can a component be replaced by another without compromising the correctness of the system as a whole? A convenient way to reason about safe replacement of a component in a system is session subtyping. The original subtyping for session types was synchronous in nature, and it only allowed to have covariance and contravariance for output and input respectively. So you could have a subtype that sends fewer messages or a subtype that is ready to receive more messages. And what asynchronous subtyping brings on the table is output anticipation. So you can anticipate non-blocking actions such as output. So for instance, in a system where you might wait for a video, so a large file, and then possibly send some information and some audio file, you could actually use asynchrony to swap these send and receive actions. So we could refine this component by this one, where here I'm sending the information and the audio first and then receive the video. And both of these components can interact with their partner without any problem. So all messages that are sent are received and no participant is stuck in the receiving state. Now let's look at another example in the domain of space telecommunication. So say we have a ground station and a spacecraft that communicate over a full duplex link. So there is a channel upwards and a channel downwards. So the ground station sends telecommands to the spacecraft and the spacecraft sends telemetries back to the ground station. A simple implementation of the ground station could look like this. We have a loop that receives telemetries until it receives the over message. When we receive over, we break out of the loop, and after that it's a loop that is internally driven by the ground station, where we send several telecommands back to the spacecraft. And this is m times. Once we are done, we send the message done. The spacecraft is the dual. It sends a bunch of telemetries and then sends a message over, and then it's ready to receive telecommands from the ground station until they send done. So we can abstract away these sort of programs with simple automata. For instance, the ground station can be represented like this, where we have a self loop over receiving telemetries. Then we receive the over message. Then we move on to the second phase of the protocol, where we send a bunch of telecommands and then the done message. And of course, the spacecraft is the exact dual. We send a bunch of telemetries and then receive a bunch of telecommands. This protocol is not very efficient because we have a full duplex link, but we're actually using it in half duplex way. So there is a receiving phase, then a sending phase. So the data goes down first and then up. But we could actually be sending on both ends at the same time because we have a full duplex link. And one way to achieve that is to refine the ground station such that it sends messages first and then moves on to the receiving phase. And you know that in this case, even when I refine the ground station as follows, it communicates very well with the spacecraft because send actions are non-blocking. So both spacecraft and ground station will be sending messages to each other at the same time, and then they will just read data from their buffers. Now it turns out that such natural pattern is actually not supported by earlier definitions of asynchronous session subtyping. And this is because these definitions only allow the anticipation of outputs if they are preceded by a bounded amount of inputs. So in this case, we have a loop that receives. So there is a potentially unbounded number of receptions executed before these sending actions. So earlier definitions will not allow you to move to anticipate these send actions before the receiving actions. And the key is that these definitions were focused on offer message freedom. So this is the ability of all sent messages to be eventually received over all possible computation paths. And the problem is that in this specific example, there is an extreme case where the refined ground station could be looping on this loop here, so sending telecommands forever and therefore never receiving the telemetries. To address this problem, we make the assumption that such degenerate executions can actually not occur. So it would always be the case that the for loop that we've seen before actually terminates. So assuming such a fairness assumption, then we assume that correct composition means that each component is always able to reach its final state and that all messages are consumed. And this is our basis for a fair compliance between two session types. So a bit more formally, we are considering binary asynchronous session types. So these are syntactical session types that have external choice that block on receive, or internal choice that are non-blocking choices here. And these types communicate over two unidirectional unbounded FIFO channels, one channel in each direction, and these channels are unbounded. I will often represent these session types as automata, as it's a bit more intuitive that way. Now, let's talk about compliance and refinement in our setting. So things are pretty simple here. We say that a successful configuration is a configuration where both session types have reached their final state and both their queues are empty, so they received all their messages. And we say that two session types are compliant if for each of their reachable configurations, it is possible to reach a successful configuration. And finally, we say that a session type T refines a session type S if for any session type S prime that is compliant with S, T is also compliant with S prime. In other words, we can always replace S by T. And in the paper, we show that this notion of refinement is in fact undecidable. And we prove this with a reduction from reachability on Q machines, which is an undecidable problem. So now I am almost ready to give you the definition of fair asynchronous subtyping. So it's a co-inductive definition over two session types. And the idea is that if T is a subtype of S, then T can safely replace S. So it's a definition that in flavor is similar to a definition of simulation. But the key insight is that we cannot observe when an output is anticipated, moved forward, as long as it is executed in all branches of the candidate supertype. Now there is two specificities of this definition. One is that we need to record these delayed inputs. Indeed, when we anticipate some outputs, it means that we have to postpone some inputs and we need to record that somewhere. And we're doing that using contexts. And because of our notion of compliance, it is the case that a candidate subtype does not need to mimic branches in the supertype that don't have partners. So now let me just give you an intuition of three definitions that we're using in the definition of fair asynchronous subtyping. The first one is related to this notion of having partners. So a session type is controllable if there exists another session type with which it is compliant. In particular, some session types cannot reach an end state, and therefore these are uncontrollable. They don't have any partners with whom they are compliant. Next, we introduce a special unfolding definition that unfolds a session type by replacing recursion variables, by their definition, only when they appear under an output. And this is necessary to identify candidate outputs that can be anticipated. The definition is in the paper, but I'll just give you a brief example here. So say you have a session type like this, where you have a recursive definition and a variable that occurs twice, once under an output selection. So if I selectively unfold this type here, well, this T will stay the same because it doesn't occur under a selection. But instead, this one here will be unfolded because it does occur under output selection. So this is selective unfolding. And finally, we need to record these postponed inputs into a context, and we do that using this notion of calligraphic A. So these are an input context, so they consist of an external choice, which might be filled with several holes. And in contrast to earlier definitions, we do allow these input contexts to contain recursive constructs. And this is key to support the spacecraft example I talked to you about earlier. Okay, so now let's look at the real definition of fair asynchronous subtyping. Again, so it's a co-inductive definition, and we define a relation R, which is a controllable subtyping relation of a TNS. And then it's a case analysis on the structure of T. So if T is end, a final state, then the unfolding of S must also be end. If T is a recursion, we simply unfold T. If T is an external choice, then the unfolding of S must also be an external choice. And then all branches that S offers must also be offered by T. So we have contravariance for external choice here. But in our setting, we actually don't need the subtype to mimic these branches of S that are uncontrollable. So we need T to only mimic these branches that are controllable, which is why we first compute K and make sure that the branches implemented by T are a superset of K here. Okay, so next, if T is an internal choice, then we selectively unfold S so that S is massaged into the right shape. So it's possibly a bunch of external choices, nested possibly, with several holes, and all of these holes are filled with an internal choice that matches the one of T. And then we simply replace this hole by the continuation of that internal choice, and we continue co-inductively. And finally, we say that T is a controllable subtype of S if T and S are in such relation. And finally now, the top-level definition of fair asynchronous subtyping. It says that T is a fair asynchronous subtype of S whenever, if S is controllable, then T is a controllable subtype of S. So note that this means that if S is uncontrollable, then it can be replaced by any type. Indeed, if S doesn't have any partners, then any refinement will do. Now, based on that definition, we show that it is a sound characterization of refinement. So note that it's actually not complete. And this is because the covariance on outputs is much stricter in the subtyping relation. And we also show in the paper that subtyping is also undecidable. And this is again based on a proof that reduces from reachability on Q machines. To address this undecidability results, we propose a sound algorithm for fair asynchronous subtyping. And this algorithm is in 2 steps. First, we check whether the candidate supertype is controllable or not. If it's not controllable, then we know that any candidate subtype is indeed a subtype. And if the supertype is indeed controllable, then we build a fragment of the simulation game corresponding to the subtyping relation. And we construct this tree up to a certain bound, or up to seeing a node that is similar to one of its ancestors. Then we decompose this simulation tree into several subtrees, and we check that each of these subtrees is a witness subtree. And we define witness subtree in the paper, and essentially it says that it's a property of the whole subtree that recognizes certain accumulation patterns. So we can see that there are some repetitions of an input context, and this is the basis to relate nodes with each other. All the details are in the paper, and we have an implementation available on GitHub. Right, let's see this implementation in action. For now, it's a simple command line tool that takes as input session types, either via files or via direct program arguments. First, I'm going to check that the ground station refinement is indeed a subtype. As you can see, the syntax really is similar to this one here. And I'm simply checking that TG prime is a subtype of TG here. And as expected, you get through as a result. Additionally, you can also check that these types are indeed controllable using the debug flag. And the tool in this case also generates pictures that represent the simulation tree we're building that represents the internal structure of the algorithm. And this may help you understand when the algorithm returns that it cannot establish subtyping. Remember that it is a sound algorithm. Internally, we're using an automata representation of these session types, which is why they look like this. Now let's try a slightly more involved example where this spacecraft protocol is actually a replacement for this protocol. Here I get the expected results, but what is more interesting is the simulation tree I am building for this example, which is then a much larger simulation tree where I have here in blue my ancestor relation. So I've seen nodes that are similar to ancestors. And this tree is further decomposed into subtrees, some of which are finite, like this subtree here. So there is only finitely many labels here, so I can easily conclude that this one leads to an infinite subtyping relation. Instead, the tree on the left here, which is this one, is actually a witness subtree and will also lead to an infinite subtyping relation, and therefore This example is also in the subtyping relation. If you want to try out the tool by yourself, all the instructions to install it and run it are on GitHub. So to wrap up, in this work we've introduced a notion of fair compliance and fair refinement for asynchronous session types. And this led us to introduce a novel variant of asynchronous subtyping that caters for these natural but previously unsupported patterns. We show that fair asynchronous subtyping is sound with respect to refinement, but not complete. And we have undecidability results for both refinement and subtyping. And again, to address this undecidability result, we provide a sound algorithm and its implementation. That's all for now, and I'd be happy to take any questions.